Okay, we are probably good to start our QFT Spring Seminar. And today we're glad to have Jing-Yuan Chen from Institute for Advanced Study at Tsinghua University. And he will tell us about instantons and Chern-Simons and lattice Yang-Mills theory from high category theory. So please.
Yep. Thanks, Antos, for the introduction. It's very glad to be here today, visit this very beautiful and finely designed campus and talk about this work, which I'm really excited about. This work is based on two papers. This first one, a fairly long paper that discussed the background, the principle, and the mathematics behind the physical construction of lattice model. And this newer paper is a more explicit construction for physicists to actually work on the model. Oops, that doesn't work again. Okay, yes. So this work can actually be motivated from three different angles. So the first is the numerical simulation of Yang-Mills theory, which is the field of lattice QCD. It's a very practical, numerical, heavy field that does not seem to use a lot of formal mathematics. And then in this field, there's this problem of how to simulate the Yang-Mills instanton. And another field that seems to have very little overlap with the previous field is the use of category theory in physics. Traditionally, category theory appears in physics working with discrete degrees of freedom using the language of tensor categories. And it works with discrete degrees of freedom, and symmetries, and TQFT, or at most CFT. But we know the real physical world is not described by CFT or TQFT, right? There's this dynamical QFT with interesting things happening in generic energy scales. And the physical degrees of freedom in reality are continuous values, not discrete values. So we want to ask whether the use of category theory in physics can be extended beyond discrete degrees of freedom, beyond symmetry, and beyond TQFT or CFT. And yet another field that very few people work on is the foundation of QFT, like how to make sense of continuum QFT. And one of the approaches is to put continuum QFT onto the lattice and see if there's a continuum limit and so on. So these are three different areas in physics or mathematical physics that used to have not so much overlap, like the people working on them are distinct groups of people. And what this talk is about is that there's a natural confluence of the ideas from these three fields that actually you need to tackle some problem in these three fields together in order to solve particular problem in one field. Yes. So that's why I find this very exciting. So let's just be concrete what the problem is. And for now, let me motivate the problem from the perspective of the numerical simulation of Yang-Mills instanton on the lattice. So first of all, what is a Yang-Mills instanton? We know a Yang-Mills gauge field is a non-abelian connection like SUN, for example. And then F is the curvature of the connection. And this is just the second Chen class of the connection. And we know that if you integrate the second Chen class over the four-dimensional closed manifold, you'll get an integer. And this integer is in physics is called the instanton number of the Yang-Mills gauge field. And the problem now is that, okay, this is continuum QFT. The problem is how to put this stuff on the lattice. So the lattice Yang-Mills theory or lattice gauge theory has been developed by Wilson exactly 50 years ago. And the lattice gauge theory, let me briefly review how it is formulated. It has a degrees of freedom taking value in a group G. Let's, for concreteness, say SUN. And the degrees of freedom lives on each lattice link. So by lattice, if you're a mathematician, you can think of a lattice as just a cubical lattice or a simplicial complex more generally. And then on each one-dimensional cell, which is each lattice link, you have an SUN degree of freedom pictured like this, where L labels the link and GL is an element in SUN. And then, right, so this is the degree of freedom. And the partition function in Wilson's traditional lattice gauge theory is that you integrate over all possible let's say SU2 for concreteness. SU2 degrees of freedom on each link where L prime labels lattice link. So this is there's an integral over SU2 for each lattice link. So this is the total configuration space, an SU2 element on each lattice link. And then there is some weight for this path integral. And let's work with a Euclidean signature quantum field theory. Then this weight is a positive number. And roughly speaking, the weight looks like this. When this G lives in SU2, when you go across a link, you have an SU2 element. And if you go around the plaquette, you have a SU2 element obtained by multiplying the 4 G's together in the order of the arrows. And this is the Wilson loop going around the plaquette. And then let's call this Wilson loop dg around the plaquette. And you can diagonalize the Wilson loop dg, and then the eigenvalue is lambda sigma 3, and then the weight should, roughly speaking, decrease with lambda. And why should the weight of the partition function depend on the eigenvalue only, but not the eigenvectors? Because of the principle of gauge invariance. When you do a gauge transformation, this G will, when you do a gauge transformation, this G will, this dg will transform by a conjugation, it turns out. A Wilson loop will transform by a conjugation under gauge transformation. So only the eigenvalues are invariant under conjugation. So if you want the weight to be gauge invariant, then the weight should only depend on the eigenvalue. And why the weight should decrease with the eigenvalue, the physical intuition here is that because this is physics, so the choice of the weight has to satisfy what we expect for the physical intuition. And the physical intuition is that if the Wilson loop is closer to the identity, then the weight will be larger. And if it's further away from the identity, it should be smaller. So the weight, at least qualitatively, should look something like this. What is sigma? Where is sigma? Oh, this is the Pauli matrix. Yeah. So it's an SU2. So sigma 3 is the Pauli matrix. Sorry. Yeah. It's a sigma z. Yeah. 1 and minus 1 on the diagonal. So the eigenvalues are e to the plus I lambda and e to the minus I lambda. Yeah. It's a hard measure integral over SU2. Yeah, for each link, you have a hard measure. Continuous. Yeah, it's an integral over SU2. Each lattice link has a... Okay, so this is Wilson's traditional lattice gauge theory. This degrees of freedom G lived in SU2 or SUN is interpreted as a Wilson line across the lattice link, and this is the Wilson loop, and the weight will be a function like this in terms of the eigenvalues of the Wilson loop around each plaquette. And yes, and then we can see that the total configuration space of Wilson's lattice gauge theory is to have a SUN degree of freedom in each link. So the total configuration space is GL, where L labels the link, and then you just take multiple product of the G, right? So it's SUN to the power of the number of links. And if we want to define an instanton number as we do in the continuum, where given each continuum gauge field configuration or connection, you can determine an instanton number, then it seems like you should have a map from the configuration space to the instanton number, to Z. However, then we see an obvious problem. This configuration space is a connected space because each SUN is connected. So the multiple product of them is still a connected topological space. On the other hand, the integers are discrete. So if you want a map that can map to different integers, not just a single value of the integer, then the map must have some discontinuity somewhere, because this configuration space in Wilson's lattice theory is connected while the instant numbers are discrete, right? So there will be some discontinuity problem, and you know this is mathematically unnatural. And in practice, if you want to define the instanton number on the lattice using any discontinuous map, there will be some practical problem as well. So at the fundamental mathematical level, there is this unnaturalness of being discontinuous, and practically this will also lead to various problems. So this is the well-known problem in the field of lattice QCD. Is it clear what the problem is? That there's no natural definition of the instanton number in Wilson's traditional lattice field theory, because any attempt to define an instant number from this configuration space will have discontinuity. Okay, and if you work with this TQFT and so on, you are probably familiar with the group cohomology construction of either like Dijkgraaf-Witten theory, gauge theory, or of SPT lattice models. And then you actually encounter a similar problem. That is, if you want to work with this, I cannot see what's there. But anyways, so this is some group cohomology class. And if the G is a Lie group instead of a finite group, then the cochains in the definition of the group cohomology will have discontinuity. This is actually the same kind of problem as the problem in QCD. So whether you're interested in this more physical QCD or the more formal problem of group cohomology and models, you'll encounter actually the same problem. That if you want to talk about the topological stuff for a Lie group gauge theory, then you will encounter some discontinuity in the traditional definitions of things on the lattice. So that's already here, we can see that this problem and this problem are somehow related, right? So if we want to solve the problem, we need to put this problem in a same kind of perspective to solve them together. And I can also mention how these problems are related to the general philosophy of putting continuum QFT onto the lattice in order to make sense of continuum QFT. So I would say the broader motivation why we are interested in lattice QFT to begin with, why we care about lattice QFT to begin with, is this fundamental problem. I would say the QFT today is much like calculus in the 1700s, where Newton was already able to describe the physical world using calculus, like the falling apple and the motion of the celestial bodies. But what does dx mean in calculus wasn't clear back then, right? So there were many paradoxes. And only 100 years later did people figure out what dx really mean in calculus. And QFT today is similar. We use this path integral to define QFT, and we can predict many remarkable like things in a standard model, but we don't really know what this path integral means because this is an infinite dimensional integral. So we want to make sense of this infinite dimensional integral. Of course, now we have not have a full understanding of it, but at least a very good attempt was promoted by Wilson, and is to think of the theory not living in a continuum space-time manifold, but living in a lattice, a discretized space-time, so that this path integral, which is an infinite dimensional integral, becomes a finite dimensional integral, at least in a finite size space-time. It's a finite dimensional integral, so it's manifestly made sense of. And then this derivative over the space-time will, roughly speaking, become the finite difference, just like in calculus. So that's, roughly speaking, Wilson's idea. And that's the motivation at the fundamental level. And at the practical level, now the computer can understand these concrete definitions of things. Then the computer can understand what you're really talking about, and then do Monte Carlo simulations for you to simulate the physical theory. And this is where this big industry of lattice QCD comes from. It can solve many strongly coupled non-perturbative problems using lattice numerical simulations. So there is a good motivation for both the fundamental reason and the practical reason. Okay. And of course, the lattice QFT is very nice. It's a well-defined QFT, satisfies many formal properties of QFT, like locality of QFT, a unitarity or reflection positivity of QFT, and so on. But the ultimate problem of lattice QFT is whether when you make the lattice size smaller and smaller, does it converge to a continuum limit? This is the ultimate problem of lattice QFT. And in general, we don't have a concrete answer to this kind of questions. But we have numerous numerical evidence that it converges very well in the practical practice of lattice QCD. Okay, so mathematically, we have not proven this, but at least there's a good numerical evidence that this is indeed what we want. However, we know that the current definition of lattice QFT certainly is not the best thing we can do, because there's this immediate problem, which is, and our lattice instanton problem is one example of that. And the immediate problem is, in general, topological operators are lost once you put the continuum QFT onto the lattice in the traditional way. And the instanton problem that I presented just now is one example of that. But there are many other examples as well. So that means there's some systematic problem with our current understanding of lattice QFT. It's not just a coincidence that the lattice Yang-Mills has this problem. There's some systematic thing that we should improve even in our current understanding of lattice QFT in order to move towards the ultimate problem in the future. Okay. And why topological operators are lost in general when we try to put continuous valued fields onto the lattice? The reason is pretty much the same as the specific example before. So the total configuration space in the traditional definition of lattice QFT would be a local product of local degrees of freedom. So this X can be a target space or a Lie group that probably lives on for the degrees of freedom living on the vertices or living on the links and so on. But they are local degrees of freedom. And the total configuration space will be the product over each vertex or product over each link of the local configuration space X. And if X is a connected space, then this total configuration space is also connected, right? But any topological operator should have some discrete classification. So you encounter the same problem as before. Either you have a single valued map or you have a discontinuous map. Either way is not satisfactory. So that means our current understanding of thinking of the lattice QFT as having this configuration space must be insufficient, must not be the full theory, must not be the full answer or the good enough understanding of lattice QFT. Or to put it in another way, why you didn't have this problem in the continuum, because we know in the continuum configuration space, although the configuration space is infinite dimensional, but we know the continuum configuration space is actually disconnected because there can be different topological classes. For example, in gauge theory, there can be different principal bundles. And you know the connections on different principal bundles are disconnected from each other, right? One principal bundle cannot be continuously deformed to another principal bundle, right? So the continuum configuration space is disconnected, but our current understanding of lattice configuration space is connected. So there must be some problem with the current understanding of lattice QFT. Is it clear what the problem is? Okay. Yeah, so the goal is to tackle this problem in general. And roughly speaking, what we need to work on still, we want to make this undefined infinite dimensional integral a finite dimensional integral by putting the theory onto a space-time lattice. But it's not done in such a naive way that we replace the derivative by differences. Okay, this seems to an intuitive thing to do in calculus, but you need to conceptually refine this step. So what we're going to do is not by naively doing this. We need to refine this. So that's the rough answer, and we'll see how that happens. So that finished the introduction to the punchlines of the talk or the motivation of the talk. And then this main body of the talk will be organized as the following. I will first start with some physics-oriented description of things, and then I will talk about a more mathematical perspective towards the end. I will begin with the known examples. So there are known examples where the topological operator problem has been solved. And those models are known for 40, 50 years. And we are going to take some general lessons from these models. And then we will ask why, while those known examples has been there for 50 years, but why people wasn't able to generalize them. There's some intrinsic difficulty of generalizing them. And then I'll describe first in explicit or physically intuitive terms how to work through the difficulty to do the generalization. And then I'll talk about how that generalization actually has a foundational origin in higher category theory, right? So why for 50 years people was not able to come up with a generalization? And that was because people didn't move to the perspective of category theory. But once you move to the perspective of category theory, the generalization will be very straightforward. Okay, so let's begin with the known examples where the topological operator problem has been solved on the lattice. Right, so we said this general problem is that the total configuration space is a product of local degrees of freedom that takes value in X, and then you have many copies of X on each vertex or each link. And then this map will either be single valued or discontinuous. Let's look at the simplest situation of this, where X is just S1. So you have a degree of freedom taking value in S1 on each lattice vertex, okay? So the total configuration space is just a product of S1 for all the vertices, which means the total configuration space is S1 to the power of the number of vertices on the lattice. And then you want to map to the topological number, which is obviously the winding number of S1, and then you will encounter this problem. Let's make it more concrete. The S1 non-insigma model, or also called XY model in physics, has such a partition function, where you have a degree of freedom, theta, that lives from minus pi to pi. So it's a U1 degree of freedom on each vertex V prime. And then the configuration is you integrate over all such configurations. And then there will be a weight on each link of the XY model. And the weight is a function of e to the I d theta, where d theta is the difference of the theta between the two neighboring vertices across the link. Okay, so this e to the I d theta is the difference between these two angles. And so this is just cosine d theta. And then because this d theta is a periodic, it's 2 pi periodic, right? So your weight is positive, and it's increasing with cosine d theta. Okay, so it's increasing with cosine d theta. So in terms of d theta, it's a periodic function like this. Okay, so that's the property of the weight. The physical intuition is that if these two angles are closer to each other, then the weight will be larger. And if the two angles are more different from each other, then the weight will be smaller. Okay, so it's a very intuitive physical QFT model or statistical model. Okay. And yeah, and let's see what the problem is. So let's consider we have a one-dimensional lattice. Say the one-dimensional lattice forms a loop with 6 vertices, for example. So this is the one-dimensional lattice space-time, a one-dimensional loop with 6 vertices. And then let's say the theta configuration, one of the theta configuration looks like this, where the direction of the angle is theta. And then another theta configuration looks like this, okay? So you should feel that these two theta configuration should have a different winding number, right? This seems to have a winding number 1, and this seems to have a winding number 0, right? That's intuitively what you expect. Yes? Is it all clear what this picture means? Yeah. However, if you think more closely on the lattice, these two configurations can be continuously deformed to each other. right? For example, if you want to deform this configuration to this configuration, you just slowly turn each theta. Let's say you turn this theta to this value, and then you turn this theta, this value, just vertex by vertex, right? You just turn this theta one by one. You can continuously deform this theta configuration to that theta configuration, right? But if you think a winding number is a topological number, it should not jump when you do continuous deformation, right? So that means the winding number has no natural definition if you say this winding number is 1, this winding number is 0, because they are continuously deformable to each other on the lattice. Yes, is it clear what the problem is? Okay. Yeah, so let's see how this problem has been, yeah, okay, so this is a manifestation of the aforementioned problem. And let's see how the problem has been solved before in the V-line model. The V-line model says, we don't say the winding number of this configuration is 1 and the winding number of this configuration is 0. What we say is the winding number take value 1 with high probability in this configuration, but it also has some low probability taking other values. And this configuration has high probability with winding number 0, but low probability with other values. Okay, but how does the probability come in, and why it makes sense to talk about probability? Okay, so that's the place where the lattice QFT starts to make a more systematic relation to continuum QFT. And that's where the key physical intuition comes in. Let's now think of the lattice as being embedded in the continuum. So the lattice loop is embedded in a continuous loop, okay? Then these vertices are just points in a continuous loop. And what will this link become? This link will be nothing but a path in the continuum loop, right? This link will be a path in the continuum space. And then you will ask a very natural question. If this link is a path in the continuum space, how does theta gradually interpolate from this value to this value when you move from this point to this point, right? That's a very intuitive question to ask. Then you will see there should be different ways of interpolation, okay? Let's say this theta is here on the circle, and this theta is here on the circle. Then along this path, the theta can interpolate like this, it can interpolate like that, and it can even interpolate like going around a few circles before reaching here, right? There are different ways of interpolation. Given that the theta starts here and ends here, like starts here and ends here, there are different ways of interpolation. And let's call the interpolation length gamma, okay? So gamma takes some negative value here, small negative value here, and large positive value if you do this interpolation, okay? So theta is just the interpolation of, it's the integral of d theta across this continuum path if you think of the model as being embedded in the continuum. Then this gamma, the interpolation length, should be a real number instead of a U1 number, right? Because while the U1 part of this gamma and this gamma are the same, but they actually differs by 2 pi, yes? The interpolation length. Yes. So actually you should introduce a real number gamma that is subjected to this constraint, that e to the I gamma is given by e to the I d theta. But the 2 pi z part of the gamma is not fixed, okay? So this gamma can be parameterized like this. For example, if you fix theta from minus pi to pi, then this m will be well-defined. Or if you fix theta from 0 to 2 pi, this m will take some other values, but the gamma is still well-defined, okay? So this gamma is a real number that can be parameterized like this with some integer m. And then we should sum over all possible integer parts with suitable weights, okay? So that is the physical intuition behind the V-line model. And later I'll talk about what's the mathematical or the categorical foundation behind it. But the physical intuition that people came up with 50 years ago was actually what led to the category theory perspective, okay? So once you introduce this gamma, first of all, let's see that this winding number becomes well-defined. Because this gamma is exactly which path you interpolated across, right? So the winding number obviously should be defined as the sum over gamma on all the links around the loop. And then this sum over gamma on all the links around the loop will be the winding number because gamma is how you interpolate it. And then because gamma is parameterized, because gamma is parameterized like this, when you sum over the gamma, the theta on the neighboring vertices on the neighboring links will cancel out. And all you are left with is that the sum over gamma is equal to sum over the integer m, which is manifestly an integer, okay? So this winding number is, first of all, a manifestly well-defined integer. And let's see how this winding number integer is related to the theta configuration. Then we need to know how this partition function of the refined V-line model is written down. So in this V-line model, the path integral is not only integrated over the theta in U1 value on each vertex. You also need to sum over all the possible integers m on each lattice link with some suitable weight that is a function of gamma. And the purpose of this part is that it should recover the previous weight of the XY model, roughly speaking. Because previously in the XY model, this is the weight of the XY model, right? Here you don't have this M and you don't have this W1, you have a weight of the XY model. And now with this, we should, roughly speaking, on each link, you should recover the weight of the XY model. And it works like this. The XY model weight, which is a periodic function of e to the I of d theta that looks like this, should be able to decompose into a sum of many terms where the sum is when you take the sum over different integers m. So each w is something that looks like a Gaussian. It doesn't have to exactly be a Gaussian. Okay, it's just qualitatively a Gaussian, but there can be some subtle difference and doesn't affect the physical behavior of the model. Yes, yes, right. So it weighs all possible integer part of the gamma, which is the weight of all possible holonomies, indeed. Yes, so the sum of the different possibilities will recover the periodic function in d theta. But W1 itself is a function of gamma that, roughly speaking, looks like a Gaussian. Okay, it doesn't have to be a Gaussian exactly, because that will not affect the physics if you change a little bit of the details, right? So that's how it works, the weight. So by summing over m, you recover the original model to an arbitrarily good precision that you want. So that's how the V-line model works. And because this m is going to be summed over, when you sum over the m, it will generate a probability profile of winding number for each theta configuration. Okay, because the winding number is determined by m, right? If we see a previous slide, the winding number is determined by m. And m and theta has some joint probability through this gamma dependence, right? So for each given theta configuration, the winding number is not determined by theta, but determined by m, okay? The winding number is determined by m, but not by theta, and theta and m has this joint probability through this combination gamma, where each W gamma looks like a Gaussian, okay? But V-line model allows us to do more than just recovering the XY model, because now you can write extra terms that were not present in the XY model. For example, we can define a winding number if we are in 2 dimensions or higher. Previously, I only considered 1-dimensional lattice, but we can also apply the model to 2 dimensions or higher. Then you consider plaquette P, and then you want to consider winding number around the plaquette. What is a winding number around the plaquette? It's nothing but a vortex around the plaquette. I guess we can imagine that. If you have a winding number around the plaquette, that is like you have a vortex in the middle of the plaquette, right? Because a vortex is nothing but a winding number around some place, right? So the vorticity on a plaquette is defined as the winding number around the plaquette, which is an integer. And then we can introduce a weight that is the vortex fugacity. For example, it can be some Gaussian in the integer valued vorticity, or it can even be a delta function that enforces the vorticity to be 0 or something like this. So you can control the probability of having a vortex on each lattice plaquette, okay? You can control the probability of the vorticity. and or even enforce it to be a delta function, like enforce the vorticity to be 0 on each plaquette. That's something the original XY model cannot do, because the original XY model does not have a natural definition of the winding number or the vorticity. So you cannot talk about directly controlling or even forbidding the vorticity in the original XY model. But once you do the V-line model, you do this refined model, you can explicitly define the vortex, and then you can discuss the controlling of its probability or enforcing the or forbidding it. Okay, so that's why this V-line model allows you to do much more than the original naive traditional XY model. Yes. D means if you're in this cochains, it's the delta in the cochain. So M is like an integer one chain, right, in mathematical terms. Because M takes an integer value on each lattice link, it's like a integer valued one cochain. Integer valued one cochain, and this D is just a delta. Or more explicitly, it's just to sum over the M around the plaquette. Okay, do we have a chalk? Okay, thanks. So we said the winding number around the loop, let's say a plaquette has a loop around it, right? So we said the winding number around the loop, is the sum over the links of the gamma over 2 pi, because the gamma is the interpolation length. So yeah, and because the theta part cancel out, it's also equal to the sum over integer m on each link. And it's a directional sum. So if you reverse the direction of the link, you need a minus sign. Okay, so when you go around it, you use this direction. You sum over m in this direction. So and if the winding number is occurring around the plaquette, then you define this winding number as the vorticity around the on this plaquette, and it's manifestly an integer because m is an integer. Yes, the winding number around the plaquette is Vp. But if you have just like a torus with, like, this is a very large lattice, and then this winding number is in general W. But if you have a W around a single plaquette like this, then it's Vp. But you can also have W around non-contractible loops. Yeah. Like the boson-vortex duality, yes, I will mention that. Exactly, once you have this V-line model, you can derive you can have an explicit derivation of the boson-vortex duality. And if you use a delta function to forbid the vortices, that's like in string theory, you forbid singularity, then you can derive the T-duality as a special case of the boson-vortex duality. And those things are all known in the 1970s. Also in condensed matter, the boson-vortex duality is derived on the lattice in the 1970s. And if you take this limit where this vortex fugacity becomes a delta function, which means you enforce the Vp to be 0, that's like you enforce that when the string wraps around a circle, you cannot have singularity. Then in that special case, you can derive the lattice version of T-duality. And this stuff are known to condensed matter theorists in 70s or 80s, and I think also known to Kleblov and David Gross in the 90s. Yeah. Yeah. But I'll not talk about the derivation of those duality, but those are very simple exercises that you can do on the lattice. So I think this shows the power of this lattice model, that you can derive many important things just doing very simple calculations. Yeah. And the reason is because you can define these topological things very manifestly on the lattice in a manifestly local manner. Okay. Previously, I talked about the S1 non-sigma model. We can also generalize the idea to a U1 gauge theory instead of an S1 non-sigma model. And it's very simple. So previously we have this S1 degree of freedom, the theta on the vertex, right? Now we just put the U1 degree of freedom onto the link instead of the vertex, okay? So previously we have a theta from minus pi to pi on each vertex. Now we have a U1 value gauge field A from minus pi to pi on each link, okay? Just put it on one higher dimension. The degree of freedom on the vertex becomes the degree of freedom on the link. So that will be a U1 lattice gauge theory. And previously we have this real valued gamma on each link, right? The gamma is interpreted as like on each link, the gamma is like how it interpolated from this angle to this angle, okay? Or like this gamma is interpolated like, or maybe it interpolated more cycles before getting to here. Like these are different gammas, right? These two gammas differ by 2 pi. So previously we have that real value gamma interpreted as this interpolation along the link. And now we have a real valued flux F on the plaquette, not on the link, so in one dimensional higher. And the physical intuition is this. If you consider Wilson loop, if you think of the lattice, again, you think of the lattice as being embedded in the continuum, then this lattice plaquette will be a surface in the continuum. And you consider Wilson loop originally started off very tiny, then the holonomy around the Wilson loop will be the identity on the circle, on the unit circle. And then if you increase the size of the Wilson loop until the Wilson loop matches the plaquette, then the holonomy around the Wilson loop should interpolate from the identity to whatever e to the I dA around the plaquette. So again, there will be some interpolation along the U1 circle, okay? And then again, there should be different ways of interpolation. And that different ways of interpolation is captured by the real valued F. So it's similar to the non-infinite model before, just by putting everything in one higher dimension. And then the winding number of the S1 non-infinite model in 1D now becomes the Dirac quantization of flux in 2D. That the sum of the U1 gauge flux around the closed 2D surface will be a multiple of 2 pi, the Dirac quantization. And that captures the first Chen class of the U1 gauge bundle. Just put everything in one higher dimension. And the vortex in 2D now becomes a monopole in 3D. Like previously, it's a vortex is around if you go around the loop around the vortex, you have a winding number. Now, as you go around the sphere enclosing a monopole, you have a Dirac quantized flux. Okay, so yeah, so just put everything in one higher dimension. And with this U1 valerized gauge theory, you can do a lot of interesting things, such as lattice abelian instanton, as well as lattice U1 Chern-Simons Maxwell theory, where you can see the chiral edge mode and all the topological stuff. And it's fully analyzed in this recent work with a student. Yeah. Okay. Wild semi-metal? Wild semi-metal is a fermion, right? Theory. Yeah, that has been put on the lattice, but I would say it's not the same as defining chiral Chern-Simons Maxwell theory. Yeah, but you are saying whether there's some similar idea, you can remove the doubler, and you cannot remove the doubler. Yeah. But you can show that this U1 Chern-Simons Maxwell theory has chiral edge mode, has gravitational anomaly, and we are also doing computation for the framing anomaly. Yeah, so this theory is indeed chiral. Yeah, so there are lots of interesting things you can play with this villainized U1 gauge theory. And then there are also a lot of more variants of villainizations in more general models, such as even for non-abelian gauge theory, you can do some villainization. And we will see momentarily what villainization really does. Previously, maybe some people have some wrong impression that the villainization is to deal with U1 in particular, and that's not true. And we'll see momentarily what villainization really does. Yes. Yeah, it's manifestly UV regulated on the lattice. And you can solve, because this is a free theory, right? It's a abelian Chern-Simons is a free theory. You can solve and see the chiral edge mode and see the gravitational and framing anomaly and stuff. Yeah, in a manifestly UV regulated manner. I would say, although the results in these works are all known in the continuum, but you know, in the continuum Chern-Simons theory, you need to, okay, when I do this calculation, I need to put in a regulator here. When I do that calculation, I need to put a regulator there, do many strange things. But on the lattice, everything is defined from the beginning. Once you have defined the theory, you don't need to put any regulator or anything else in the calculation. You just do the right calculation and extract the right physical quantity and interpret it. Yeah, you don't need to put regulators anywhere. So I guess this is still valuable, that although it doesn't have new results, but it gives a manifest UV regularization of all the known results. Yeah. Yeah. Right. So let's see what the villainization really does. So we have, as we'll see in this development of this more general framework, we'll always have two perspectives, a geometrical perspective and an algebraical perspective. And these two perspectives will be unified in the language of category theory. But for now, they appear as somewhat different perspectives, okay? And the geometrical perspective is what we described before, that you think of the lattice as being embedded in the continuum. Then you think of how this angle interpolates to this angle when you gradually move along the path in the continuum. And then it will give a path in the S1, okay? And yeah, so this is some very important physical intuition that will be important for a lot of the generalizations later. And the algebraic perspective is also very useful. Algebraically, what we have really done is that we have a S1 degree of freedom, and we are interested in the topological configurations characterized by pi1 of S1, right? The winding number. But when you put on the lattice, there's this discontinuity problem that we mentioned before. So what do? You find a universal cover of S1, which is R, and then by the long exact sequence of homotopy groups, the pi1 of S1 is isomorphically captured to the pi0 of Z, which is just counting integers. And that would not have discontinuity because Z is discrete to begin with. So that will not have discontinuity on the lattice. So this is just the simple algebraic structure behind the Villain model. And this R is what we call gamma subjected to this constraint. And this map from R to S1 is indeed this map, okay? So this is algebraically what Villain model did. So from here, you can see that Villain model is not to work with U1. What Villain model does is to capture pi1 of anything, okay? Pi1 of any space. As long as you have a target space or a Lie group whose topology of pi1 you are interested in, you find it's universal regardless of whether it's a abelian or non-abelian, or it's not even, doesn't have to be a group. It can be a general target space like RP2 or something. You are interested in this pi1 topological configurations on the lattice, you go to its universal cover and just do the same thing, okay? Right. So this is what the Villain model really does. It captures pi1 of things onto the lattice. And through either perspective, or through the lesson of Villain model, we kind of get a general picture of what we should do. So we have the traditional fields, which is this theta taking value in S1. And what we do is we introduce some new fields. Instead of determining a topological number directly from the traditional field, which will suffer from discontinuity, you introduce some new fields. Some of them are discrete. And then the discrete part of the new field will determine the topological number, okay? And how is the topological number related to the traditional fields? The new fields and the traditional fields have some coupling or some joint weight in the path integral. So the traditional fields will determine the topological number probabilistically through this joint weight, okay? So that's the kind of the philosophy. And what is the principle behind the introduction of these new fields? Intuitively, the introduction of this new field should recover the desired homotopy information in a continuum, like how, when you think of the lattice as being embedded in the continuum, how the theta here interpolate to the theta there. Okay, so the new field should somehow recover that homotopy or interpolation information. That's the physical intuition behind this construction. Without going into the details, I would say there's another known class of models, the spin-on decomposition of S2 non-integral model, or more generally CPN non-integral model. Well, S2 is CP1, where you can also do similar things and define the topological configuration of S2 non-integral model captured by pi2 of S2. Okay, I'll not go into the details. But algebraically, so this is some geometrical perspective of how it works, and I will not explain that because of the time limits. But algebraically, that's how it works. So this is how the V-line model works. It captures the pi1 of S1 or whatever to pi0 of Z or whatever through going to the universal cover. And this model is, in order to capture the pi2 of S2 or CPN, you go to the 2 cover, like in this case it's SU2, and then you get a U1 degree of freedom, just like the M before. Now you get a U1, and the pi2 of that S2 will be captured by the pi1 of U1. I guess this is familiar in high energy physics, that if you have a SU2 gauge theory, and the SU2 gauge theory is completely Higgs by an S2 non-integral model, then we have a residual U1 gauge field. Okay, so this U1 gauge field is interpreted as the Berry connection of this S2 non-integral model, if you're familiar with what a Berry connection is. And then you further villainize the U1 gauge field, as we talked about the U1 gauge theory before, right? So you further villainize it, then the pi1 of U1 is further captured into the pi0 of the Z. And then that will be the Berry curvature, and that will be the skyrmion, and so on. So that's how it works for pi1 and pi2. And those are the only known examples of the previous constructions that how people capture the topological configurations of continuous value degrees of freedom onto the lattice. And we will see momentarily why it is difficult to generalize beyond the pi1 and pi2, okay? But those are the known examples. And indeed, the known examples follow such a philosophy. So now let's talk about the difficulty of going beyond the known examples. Okay, this is the algebraic perspective of the known examples. And it seems very obvious what you wanted. If you want to capture pi3 of something, what you need to do, right? You just extend this ladder one step further, right? That seems what you need to do. Okay, so indeed, it looks like if you want to put a non-integral model with value in SUN, for example, S3 non-integral model that describes pion. So the pion is a SU2 or S3 non-integral model, right? Or if you want to put the SUN not on the vertex but on the link, so that you get a gauge theory, then and then you also want to capture the pi3 physics, then it seems just by naively generalizing this principal bundle pictures, it seems you need to do this. Yes, that's all you need to do, and capture pi3 of this and to pi2 of something, and so on. So I explain the problem, and it's sort of very obvious what the problem is actually. So I guess people in the past, they have written down these models, but they haven't put these models in these perspectives. They just wrote down these models by their physical intuition. But once you organize these models in this language, it's obvious why people could not generalize it further in the past decades. And the reason is following. Let's consider SUN non-integral model. That means the SUN, for example, SU2 degree of freedom, lives on each lattice vertex. Then we even have some good interpretation of what this U1 and this stuff are. So in the non-integral model, this U1 will be the West-Zumino-Witten curving, which is a two-form generalization of the Berry connection, and this will be the West-Zumino-Witten density, which is the trace G inverse dg cube West-Zumino-Witten density, and that will be the skyrmion in the non-integral model. And then if you are in gauge theory where everything is in one higher dimension, then this West-Zumino-Witten curving two form will become the Chern-Simons three form, And this R will be the exterior derivative of the Chern-Simons 3 form, which will be the second Chen class or the trace wedge wedge F4 form, okay? And then this Z will be the instanton number, okay? You even have good interpretation of what these things are intended to correspond to in the continuum while they live on the lattice. But the problem is, let's focus on a non-infinite model. So we will look at the Witten and stuff case. Then this will live on the lattice vertices. And these question marks will live on the lattice links for the non-infinite model. And it seems like on the lattice link, the degrees of freedom should be able to compose. Because as we said in the lattice gauge theory, it seems like you should have some link degrees of freedom. And as we introduced at the very beginning, the link degree of freedom, people are used to the link degree of freedom being some group element. And when you go around the loop, you compose the group elements, right? So it feels like the link degrees of freedom should be able to compose. Then traditionally, people think about groups. However, we need the pi2 of these double question marks to be isomorphic to pi3 of SUN, which is Z. But we also know that finite dimensional Lie groups always has trivial pi2, right? And the whole point of working with the lattice theory is to make everything finite dimensional, as we said from the beginning. So that is the simple reason why traditionally people have not worked out the generalization that captures pi3 onto the lattice, because any finite dimensional Lie group doesn't have non-trivial pi2. So that's why they couldn't come up with a simple generalization of these previous models, okay? Actually, if you know the final resolution to this problem in terms of category theory, you'll know that even if you don't care about this being a Lie group, as long as these are principal bundles or as long as these are fiber bundles, you're not going to be able to solve the problem even using fiber bundles, regardless of whether this is a Lie group or not. But I will not explain why that is the case. But just in principle, this sequence of fiber bundle idea just doesn't work if you want to capture pi3 onto the lattice in a finite dimensional manner. Okay? So yeah, the conclusion is this philosophy that we learned from the V-line model actually still works. And we also know how it works for pi1 and pi2 topological configurations. And it works through principal bundles. But for more general cases, it's mathematically impossible for group theory or fiber bundles to fulfill our goals. That is, the new degrees of freedom and traditional degree of freedom should not form any fiber bundle or any Lie group and stuff. Okay, we need more general, more flexible game rules. And then we need to work with higher categories like the simplicial sets and Kant complex and stuff in order to be able to complete this goal in a finite dimensional setting. So the idea is that this new degrees of freedom and the traditional degree of freedom should form a finite dimensional higher category, and it's a simplicial version of weak higher category in order to recover the desired homotopy information in a continuum. You cannot accomplish this using principal bundles or groups anymore. Okay, so that is the reason why in the past decades, those V-line model and the spin-on decomposition model has been known for 50 years, but people was not able to generalize further because people didn't think beyond the familiar toolbox of principal bundles. Okay. Yes, so this will be formulated in terms of gerbes. Yes. Yeah. And we need finite dimensional and suitable versions of gerbes to have nice enough properties. And that's what I'll introduce. Yeah. So so in general, we need coverings that are not fiber bundles. And also we need the degrees of freedoms to be able to compose, but the result is non-unique. For example, when you compose G and F, we can compose it to one possible result is H through the composition psi. But we can also compose to some other result H prime, and we can talk about the relations between H and H prime, okay, through some relation phi. And if you can recognize that this is some picture in category theory, like the simplicial version of category theory, okay? Yeah, and maybe you are familiar with some ideas like this. Right? In anion fusion, the fusion of two simple anions is not a unique simple anion, right? It's many possible simple anions, and there are different fusion channels. And indeed, this language, as we'll see, this language can cover the language of tensor category description of these anions when the degrees of freedom becomes discrete. But the key point is our language can also work for continuous degrees of freedom. And that's what the tensor category language or fusion, whatever, cannot achieve. Yeah. So yeah, so that's why I'm very excited about this. Okay, and if you're not very familiar with category theory, I would say this is very much like playing a board game like Settle of Catan or something, where, okay, maybe you have built some roads and some wood lines and then some river somewhere on the lattice links on the board. You never need to know what a river composed with a road means, right? It doesn't mean anything. A river and a road is just river and a road. You don't need to talk about what they compose to. But you can ask, okay, under this rule of the game, what type of castle is allowed to be played here, and what are the advantage of each type of castle can bring you, right? You can play that game, the computer can play that game, and that kind of idea is what this simplicial weak category is all about. You don't talk about a composition of things. You just talk about, okay, you already have these degrees of freedom on the links. What degree of freedom you can put on the plaquette? You don't need to be able to talk about the composition of things into a certain result. So that's the more flexible rules of the game. If you can play these games and the computer can play this game, the computer can also do Monte Carlo for the categorical model of lattice QCD. Yes. Okay, let me briefly explain the main construction just in a physically intuitive manner before I go to the more systematic category theory perspective. So this construction of the S3 pion non-exam model as well as the SUN Yang-Mills. So this is where the S3 or SU2 degree of freedom living on vertices. This is where the this is where the degree of freedom living on the links. And yeah, the mathematical structure to describe this thing has many names because people develop this structure from different perspectives. Okay, multiplicative bundle gerbe, principal two bundles over Lie group, or Lie two group extension, and stacks. Okay, there are different names for these things. And explicitly, the model works like this. Let's consider a S3 non-exam model. So, or let's say SU2 non-exam model. So you have the traditional degree of freedom where you have an SU2 degree of freedom living on each vertex. So that's the traditional lattice non-exam model has. Each vertex has a SU2 degree of freedom. And then now we want to capture this topological stuff. In 2D, we want to be able to describe the Wessel-Minor-Witten term in 2D. In 3D, we want to be able to talk about skyrmion, which is actually the nucleon, if you think of the S3 non-exam model as a model of pions. The skyrmion will correspond to the nucleon, the protons and neutrons. And in the 4D, you have the non-conservation of nucleon, which is the 4D hedgehog. And you want to be able to, for example, just like the vortex fugacity just now, you want to be able to impose a delta function that forbids the non-conservation of nucleons, if you think of the nucleons being conserved in your physical model. And all those are captured by pi3 of S3 equal to Z. Okay, so to capture those topological configurations beyond the traditional SU2 degree of freedom on each vertex, you need to introduce new degrees of freedom on each link. And in particular, the link degree of freedom, if you want the link degree of freedom to be finite dimensional, as we'll introduce, is a finite dimensional degree of freedom, then it cannot be a group and it cannot be a fiber bundle either. And then you introduce some link weight. And then there will be a plaquette degree of freedom. And the plaquette degree of freedom is a U1 value. And this U1 value will describe the U1 value Wessel-Minor-Witten curving tool form. It's a lattice correspondence of the U1 Wessel-Minor-Witten tool form. And then there is some plaquette weight that will determine the saddle point of the Wessel-Minor-Witten tool form. So the Westermino-Witten tool form is an independent degree of freedom, but will have some weight. So it has some saddle point and with some probability. Okay. And finally, you valenize the U1 valued Westermino-Witten tool form. And then it will have an integer value, just like the integer value thing in the V-line model before. And you have some cube weight over the skyrmion, or say the nucleon or baryon density. And finally, you have some hypercube baryon non-conservation fugacity. For example, you can control the probability when the baryon or the nucleon is non-conserved, or you can make this a delta function so that the baryon or nucleons are conserved. Okay. So the model, roughly speaking, looks like this. And I guess, what is the time now? Okay, maybe if we have some extra time, I will introduce the model more explicitly. But now I just want to show you that there are the traditional SU2 degree of freedom on each vertex for a SU2 non-decimal model. And then there are some non-group or fiber bundle valued degree of freedom, but you can still describe them manifestly on each lattice link. And then there's some U1 WZW2 form degree of freedom on the plaquette. And then there's some integer that valenize the U1 degree of freedom on each cube. And there are some suitable link weight, plaquette weight, cube weight, and hypercube weight on each dimensional lattice cells. And all these degrees of freedom together will form some bundle gerbe structure. And if I have more time, I can go through this idea of the construction of the degrees of freedom and the weight. But since I don't have much time, let me skip the details of the model first and go to the more systematic understanding of how this is related to ideas in TQFT. But before that, I also want to say, if you want to, so previously that was for a non-decimal model, S3 or SU2 non-decimal model. And if you want to go to Yang-Mills theory, where you want to describe the 3D Chern-Simons 3 form of 4D instanton or 5D Yang monopole, which is a non-conservation of instanton in 5D, then you just roughly speaking, put everything in one dimension higher. Like the link degree of freedom now take value in SUN, and this plaquette degree of freedom now take value in the thing that is not group value or not fiber bundle value that described before. And the cube degree of freedom is now U1, and it's interpreted as the lattice version of Chern-Simons 3 form. And the hypercube has an integer that valenizes the model, and we get instanton density. And it's related to the SUN non-decimal model via categorical procedure called delooping. But roughly speaking, it's just putting everything in one higher dimension. But that procedure has some non-trivial thing that you need to work out. It's that the process of going from a lattice non-decimal model to a lattice Yang-Mills actually involves solving a Yang-Buster equation, which is just like braiding in TQFT. And in general, Yang-Buster equations are very difficult to solve. But the nice thing is it's automatically solved if we use some physical intuition from the continuum to help us build a model. Okay, I don't have time to go through the technical construction of the model, but I just say it's very nice that to define Yang-Mills theory in a refined manner on the lattice, you need to solve some Yang-Buster equation, and the equation is automatically solved if you use some good physical intuition. Okay, so that's the punchline of the construction without going into the details. Maybe let me use the rest of the time to talk about the category theory perspective, how all these things are motivated. Again, we'll take two routes. So there's this desired continuum degree of freedom, which is the continuum non-decimal model or continuum gauge theory or like principal bundles. And then we want to figure out what are the lattice degrees of freedom that we really need beyond the traditional lattice degrees of freedom. Okay, we have two routes to solve this problem. One is we first decide what are the algebraic topology data that we want from the desired continuum QFT. And then we use the geometrical picture to help us realize that algebraic topology data onto the lattice. Another route is that, okay, this continuum degrees of freedom, of course, gives us some geometrical picture. And then we use the algebraic topological data to help us truncate the geometrical details to some lattice degrees of freedom. Okay, both ideas give the same result, and they are unified in the purview of category theory. Let us briefly introduce the algebraic topology data route to begin with. So previously, we said the V-line model taught us this philosophy, where instead of defining a topological number from the traditional fields, we need to introduce some new fields that form some joint degree of freedom with some traditional fields that forms some higher category that covers the desired homotopy, information, and continuum. And we use these new fields to determine the topological number. Mathematically, what is this idea mathematically? What is this philosophy from V-line model, really? It is actually this. Now, okay, I draw the arrow from the right to the left. So the previous picture, the arrow is from the left to the right. Sorry, but in this picture, the arrow is from the right to the left. Okay, so the traditional fields are here, and the desired topological numbers are here. And we want to have a map here. And we know that there is the map is either single valued or discontinuous. We cannot get what we really want. And in the category theory, it turns out that the traditional fields actually take values in a category, and having such a map is actually to have a functor from the category of the traditional fields to another category that describes the desired topological classes. And having this problem means there's no nice functor. Okay, there's no continuous functor from the category of the traditional fields to the category of the topological numbers that we want. However, it is well known in category theory that when we deal with continuous degrees of freedom or continuous categories, which means categories where you not only care about sets, but you also care about the topological structure or the smooth structure on the set, then functors is not a good notion. In general, you should consider the notion of anafunctors, which has also many names in specific fields, but the general name is anafunctor. And the idea of anafunctor is instead of considering a direct functor from this category to that category, you construct a larger category, but in some sense equivalent to the original category. So you have some category that's larger, you put it in the middle, it's larger than the original category, but somehow equivalent. And this larger category will have a direct functor to this desired target category, okay? And this category in the middle is indeed where you have the traditional fields as well as the new fields, okay? So this is the philosophy of the V-line model developed by, oh, by the way, the V-line model was originally developed by Berezynski, but Berezynski died very young, but he and Kostelis and Saulas discovered this PKT transition, which was awarded the 2016 Nobel Prize, okay? So Berezynski, through his physical intuition, did some very important physical work by developing this V-line model and discovered some very important physical effect. And the philosophy can be turned into mathematical language of anafunctor. Okay, so that is what we extract from the philosophy of Berezynski's V-line model. The right-hand side is actually, so because in the slides I didn't have the details because we will not have enough time. But the right-hand side is this. In the traditional non-sigma model, the category is this pair category. T is the target space, for example, S1 or something, like in the non-sigma model is S1. And then this is the topological space of objects is S1 in the right. So, and this is the topological space of the morphisms. It's just right. So each element is just e to the I theta and e to the I theta prime. Okay, and the source is e to the I theta. The target is e to the I theta prime. Okay, so between each two objects, there is a unique morphism. Okay, so Right. So yeah, so I can also consider lattice. The lattice will be like so, and so on. This will be the set of lattice vertices. This will be the set of lattice paths that interpolate between vertices, and that will be the lattice surfaces formed by plaquettes and so on. And then a functor from here to here will be a field configuration. And indeed, right, so each lattice vertex has a S1 degree of freedom, and each lattice link, it has a S1 degree of freedom at each end of the link, right? So we have a lattice link. It has a e to the I theta on this vertex, e to the I theta prime on this vertex. So the functor, the lattice field configuration is a functor from the category of the lattice to here. Okay. Yeah. So that's the pair. That's the group. That's the category that describes the traditional fields. And the topological number for the winding number will be BZ. The BZ, no, it's actually B squared Z, which is Z star. Why is that? Because the lattice vertices will map to nothing non-trivial, the links will map to nothing non-trivial, and the plaquettes or the surfaces will map to an integer, and that's the vorticity that we described before, right? You don't, well, because the topological thing you get is a finite, it's not an infinite category, it's a finite n category. So in the middle, in general, you only need a finite n category, right? And I would also want to mention that this category, if you're familiar with category, this category is actually equivalent to a trivial category, right? But that doesn't mean the theory is trivial. That's a very important distinction with TQFT. In TQFT, if the target category is trivial, that just means the theory is trivial. Why is it different for more general QFT? Because the general QFT has a weight. The weight might not be invariant under natural transformation. So yes, so I guess we have some discussion of this before. So when you think of this category and when you think of equivalence class, this indeed as a category or as a groupoid is equivalent to the trivial category or trivial groupoid. But what you really think, you should really think of, this is the category that describes the target manifold, and these are the identity morphisms. And you are considering an inclusion of this into here that describes the identity morphisms. So this together is an element in the under category of groupoids under T. And so you are only considering equivalences under this. So physically, that just means the category is trivial, but the path integral weight does not respect invariance under natural transformation. Mathematically, it's you need to consider groupoids under T. Okay, so that's why, although this by itself is trivial, but as a groupoid under T, it's non-trivial. And that's the difference, the crucial difference with TQFT. I guess there were, I guess that's also, if you move from the TQFT direction, that is one of the crucial part that you need to go through in order to describe the QFT in general, right? Yes. So the weight should, in some sense, the weight should respect this map. Yeah. So all this can be formulated very systematically in category theory, and they all have very physically intuitive explanation. So I guess this is a very nice bridging between the traditional ideas of QFT and the formal language of category theory. So this philosophy of the V-line model translates to the use of anafunctor in category theory. And then for our particular case, for example, we want to describe S3 non-integral model, the pion non-integral model, or SU2 non-integral model. Right, so the traditional degree of freedom is to have a SU2 or S3 on each vertex. And then on each link, you just have two copies of SU2, right? So I can, so the T times G there is like on each vertex, I have a G on the vertex in SU2 that describes a point on the S3 vacuum of the pion. And then on each link, I can have I can either have G vertex and G vertex prime, or I can also parameterize as G vertex prime and then GH link, such that G vertex prime is equal to H link times G vertex. Okay, so this will belong to the T equal to S3, and this H will belong to the G equal to SU2. Okay, it is how the GV on the S3 is rotated to GV prime, another point in S3 through an SU2 element. Okay, so this is the traditional degree of freedom in the traditional lattice non-infinite model of pions. And then those higher morphisms are the same as the one morphism, which just means there are no new information in the higher morphisms. Okay, at least all identities. Okay, and I have presented this as a simplicial set actually. I didn't talk about what a simplicial set is, but anyways, the traditional degree of freedom can be formulated in terms of a simplicial set, which is essentially the nerve of this thing. Okay, the nerve of this thing. Okay, and then the topological stuff we want to describe, the first non-trivial topological stuff we want to describe is a B cube U1. Why is the B cube U1? The U1 on the 3 morphism actually correspond to the trace G inverse DG, where G is this degree of freedom. But in the continuum, we know this 3 form. This is the Wessel-Minot-Witten 3 form that describes the topology of the stuff, right? And then if you integrate this value over a cube or over a 3-dimensional region, over a three-dimensional region on the lattice is a cube, then you'll get a U1 value, right? So that U1 value is the sort of the topological stuff you want to be able to capture. And so you just want an anafunctor from here to here, and you want to consider the classification of anafunctor from, well, again, you want to, when you say classification, again, this is a trivial category because it's just this. Again, you want to consider natural transformation that preserves this map. Okay, roughly speaking, that will be ignoring this T because this map will preserve that T. So when you do classification, you ignore that T, then this will just be nothing but the classification of anafunctor from BG to BBB U1. Okay, and then that anafunctor will be classified indeed by the group cohomology of G to U1. But now this realization of group cohomology via this anafunctor will not involve any discontinuity, and that's the whole point of using the notion of anafunctor. And this category in the middle of the anafunctor is indeed the degrees of freedom you will need to use for the refined version of the lattice QFT. Okay, so this is the classification, but you are no longer using discontinuous cochains to construct the anafunctor. Everything is manifestly continuous, and it's related to many other interesting things in mathematics. Okay, but that's roughly speaking how you systematically motivate. Given a desired continuum QFT, you know there's a problem of defining topological stuff from the traditional fields. You construct this anafunctor, and then you systematically get what you need on the refined version of the lattice. And very remarkably, so previously we talked about these degrees of freedom being SU2, right? But when you change the degree of freedom, for example, G is some finite group and T is just a set of the finite group, then this whole thing will reduce to the Dijkgraaf-Witten model when G becomes a finite group. In that case, the target category in the middle doesn't have many new stuff. Somehow you get this Y will just still be G, and this lambda will have G times U1, where this U1, and you can even recognize what this U1 is. And if you're familiar with the language of tensor category, this U1 will be the phase of the C linearity enrichment in the definition of tensor category. Okay, and this up top left map from here to here is nothing but the associator or the F symbol in the Dijkgraaf-Witten model. And more generally, you can also replace this traditional category by some more general discrete degree of freedom. Then you can describe Turaev-Viro model. And again, that U1 in lambda will describe the C linearity enrichment in the tensor category language. So although by motivating this, the whole motivation comes from continuous degrees of freedom. But when you apply it to discrete degrees of freedom, it automatically recovers the model that people use to construct from the tensor category language without having a motivation from the tensor category perspective. So I think this is very exciting. You start your motivation from describing continuous value things, but when you reduce the discrete degree of freedom, you can recover the tensor category methods model. Yeah. Yeah, so yeah, this is what is being said in this slide. And let me also briefly explain the other route of motivating the lattice degree of freedom from first having the geometrical picture and truncating the picture by the algebraic topology data. So that is very exciting for another perspective. That is, we want to systematically rethink what a lattice QFT really is. In the past, Wilson and others, they developed this intuitive understanding of lattice QFT. But now we can systematically rethink what a lattice QFT really is and what is a systematic relation to continuum QFT. That, I think, is another very exciting thing I feel about this program. So let's consider what is a field in a continuous non-infinite model. In a continuum non-infinite model, a field in a continuum non-infinite model is nothing but a map, a continuous map from the space-time manifold M to the target manifold T. And now we want to uncover what are the degrees of freedom on the lattice that we need to construct in order to describe the full information, or at least the full topological information of this continuous map. Traditional lattice theory does this. Okay, we have this map from the space-time manifold to a target category. This L0 is some vertices. We think of that as some discrete points embedded in the continuum. So these are just sampling some discrete points from the infinitely many points in the continuum, right? So you are just sampling some points on M from this function, okay? Then of course, because you are only sampling finitely many points from the continuum, you lost the interpolation information. And through the philosophy of the V-line model, we know what we sort of want to do. Let's describe that systematically. Now let's ignore the lattice for now and think about what we can play with in the continuum. Given a continuous map from M to T, we can consider this higher category of the path space of M. So this PM is just the space of all paths in M, okay? So each path in M will connect 2 points in M. So it's a morphism in M, right? So the objects are M, the morphisms are paths on M. So it connects 2 morphisms. This P square M I can consider like singular triangles in M. So it's like, or I can consider globular shaped things or singular triangles in M. So in practice, I will use this simplicial version. So this P square M are like triangles in M, and that is like 2 morphisms in M. So, and similarly to T. So roughly speaking, this is just the space M. This is the space of path on M. This is roughly speaking path between path on M, and so on. Path between path, and so on M until D dimensions, the space-time dimension. And similarly for the target manifold. And given a continuum map from M to T, you automatically induce continuum map from path in M to path in T, because each path is made up of points, right? So if you know how points in M map to points in T, you know how points in path of M map to points in paths in T, and so on. So you don't get anything new. You just seem to have a fancy language. You don't get anything new. Because once you know how the points on M map to T, you automatically induce all those maps. You don't get anything new. However, when you think about the lattice, that's where the magic comes in. Traditionally, when you sample some discrete points in M, you lost some information. Now, let's not only sample discrete points, but also sample the lattice links or lattice paths. Then the lattice paths, you think of them as continuum paths embedded in the continuum manifold. Okay, so each lattice path is mapped to some continuum path in M, and that will map to some path in T. Okay, so now you recover some interpolation information. And then you introduce the lattice plaquettes, and they map to surfaces in M. You recover more interpolation information until you go all the way up to D-dimensional cells. Okay, then you recover the full interpolation information in the continuum. Okay, so this way you recover the full information, full interpolation information in the continuum. However, this is in the end and actually a continuum QFT, not a lattice QFT, because it has the same information as the continuum QFT, right? But what you gain is a lattice perspective. You artificially think of the continuum manifold as artificially draw a lattice that discretizes the manifold. And then the continuum field has a lattice interpolation. And that's this different from an actual lattice field theory by the fact that these spaces are in general infinite dimensional, because the space of paths in the target manifold is in general infinite dimensional, right? So if you have, for example, if your target space is a sphere, T is a sphere, then the paths in T looks like this. And we go around and take all weird shapes, right? So the path space in general is infinite dimensional. So the difference of this has a lattice perspective, but the difference between this and a usual lattice quantum field theory is that in the usual quantum field theory, these higher dimensional degrees of freedom should all be finite dimensional rather than infinite dimensional. So it's obvious what we want to do now. What we want to do is we find because this is an infinite dimensional high category theory, a high category with some topological information, we just want to find a topologically equivalent, at least up to whatever algebraic data that we care about, an equivalent category, but realized in a finite dimensional manner. So it's a finite dimensional equivalent higher category, but has the same amount of desired topological information as the original infinite dimensional category. And then we will use, that finite dimensional category as the degrees of freedom on the lattice. So that is the geometrical perspective of what the V-line model teaches us and how to obtain this target category for the degrees of freedom for the refined version of the lattice model. And the nice thing is the very vague physics problem of, oh, we want to put a continuum QFT onto the lattice. We have some intuition what we want to do, but we don't know what we really are talking about mathematically. Now it becomes a well-posted mathematical problem. This, I think, is what is very exciting. That the vague idea that we want to put a continuum QFT onto the lattice, retaining the topological information, that has now become a well-posted mathematical problem. So all we need to do is to ask the mathematicians to solve this mathematical problem. Okay, yeah. So this is the perspective of using a geometrical picture and use some algebraic data to truncate into a finite dimensional higher category. Okay. Yeah. And I want to also say that this perspective of using this path space and stuff to capture the homotopy information and then truncate it to a finite dimensional weak higher category is indeed how category theory appeared in the historical development of homotopy theory itself in mathematics by these people, right? And similarly for Yang-Mills theory, there's a similar story where a field in a continuum Yang-Mills theory is described by an anafunctor from the path group point of M to BG, okay? So this map from a path in M to G is just a Wilson line, okay? So this is what we have in a continuum, and on the lattice we have a similar thing that, okay, this is an infinite dimensional category. Everything is infinite dimensional, including the classifying space BG. And now we want to truncate it to a finite dimensional category that has the same topological information. And then this is equivalent to taking a de-looping of the non-linear model thing, and that will involve some Yang-Bast equation, and it's very beautiful. Okay, so that's the mathematics behind this lattice construction. So the mathematics can be very formal, but every step has a very physically intuitive counterpart for physicists. Yeah, so let's go to the outlook. Of course, the primary purpose and what's really exciting about this is the bridging between formal mathematics and actual numerical practice. So we want in the near future an actual numerical implementation of this so that we can study the instanton physics numerically. And there are some very interesting mathematical problem. I think one of the most interesting thing that we can do in the near future is to talk about what it really means to have a higher representation of these simplicial higher groups or Kahn complexes. And what we really need is a harmonic analysis over the simplicial version of higher group. Why we need a harmonic analysis? Because we are familiar, right? For a Lie group, harmonic analysis is just representations of a Lie group. And by going to the representations, we can talk about the observables of a Lie group degree of freedom. We can also go from a Lagrangian perspective to a Hamiltonian perspective, where the canonical variable of a Lie group element is the representations, okay? So we need harmonic analysis of the degree of freedom. For a Lie group, that's what we did. So now we have this simplicial version of weak higher groupoids. What is the counterpart of harmonic analysis? I don't think a suitable notion of high representation in terms of harmonic analysis has been developed in mathematics. At least through my search, I haven't seen. Right. But there are discussions of high representations, but not along the line of harmonic analysis. So yeah, and physically the counterpart is okay, first of all, we want Hamiltonian formalism, and also we can ask the following, like for example, an SUN non-linear model, the zero-dimensional observable is the order parameter, two-dimensional observable is a Wessel-Minor-Witten insertion of level K, and the three-dimensional observable is a topological theta term with the skyrmions. But what are the one-dimensional observables? The one-dimensional observables cannot be formulated in terms of groups, but it must has a counterpart in some higher category that describes some suitable notion of high representation of the simplicial version of weak higher groupoid. So that's what we need from the general notion of harmonic analysis. So that I think is a very exciting mathematical problem that has an immediate physical application of turning this stuff into Hamiltonian formalism and describing these generalized observables. And for a gauge theory, this will be become the Wilson line. This will become the three-dimensional Chern-Simons level. This will be the four-dimensional topological theta term. And you can ask, what is the category-valued two-dimensional observable of a Yang-Mills theory? I think those are very exciting physical problems and mathematical problems. And yeah, and in a longer term, the more even more exciting things is like a unified categorical language for discrete as well as continuous degrees of freedom. At least in our construction and the recovery of the Dijkgraaf-Witten model, we see that explicitly that's what happens. But what is the big story behind that? I don't know. Also, we want to go beyond the kinematics, like people talk about symmetries, generalized symmetries, anomaly matching, and so on. All those are kinematics. But this model describes the dynamical QFT. The purpose is also to study the dynamics. So we want to go beyond discrete degree of freedom towards continuous degree of freedom, go beyond the kinematics and topology towards dynamics. So I think we should have a unified categorical language for that. And also, yeah, so there's, I think there's also some implication for constructive QFT. Constructive QFT is a very ambitious program of trying to define what a continuum QFT really is, right? It's like this millennium price problem. And Balaban has done a lot of remarkable work trying to see if a lattice QFT has convergence. So in the 80s, he showed that in Wilson's traditional definition of lattice Young-Mills, he didn't show convergence, but he at least showed there's no divergence as the lattice spacing becomes smaller and smaller. He showed that it's bounded. He didn't show convergence, but he showed it's bounded. And now we have a refined version of Wilson's lattice QFT. We refined Wilson's lattice QFT. It has more natural correspondence to continuum QFT. What are the implications to constructive QFT? And also how this categorical way of organizing things will help us organizing efforts in constructive QFT. I think those are also very important things to explore. And I think that certainly one will be able to say something along these lines. Unfortunately, Balaban's works are very, 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 very technical. And once he lost his draft papers, and he himself was not able to go back to the same field. So I think it's very hard to go into this field. But if one really goes into there, I think something could be said. So I think these are some very big excitements that I look forward to. Yeah. Unfortunately, I didn't have enough time because I need to cover the physical intuition as well as the big mathematical story behind. But if we have more time, we can discuss how that physical model is actually constructed. But I hope through this, I hope at least I have showed that there is some very natural mathematical story there. There's a natural involvement of the language of category theory, and that corresponds to very physically intuitive constructions that connects previous model to new models that can have actual numerical practice application. Okay, thank you very much.
Questions?
I recall that in continuum, by dualization, you can introduce vortex line.
Yes.
And so you have to integrate over also vortex line. Then there is constraint which makes it vortex. So you introduce additional degrees of freedom.
Yes.
So you are imagining something similar to monopoles and instantons, that there is additional degrees of freedom.
Right.
Some dualization.
Right.
You are categorifying whatever to the lattice.
That's yes.
What basically.
Yes. So that's the idea. So after you know the answer, everything is very simple, very natural. At least for people who are familiar with the homotopy theory. I think the interesting thing is that this connection between the lattice QFT and the known mathematics. Yes. Yes.
Thank you, Jing-Yuan.
Yes.
That was one of the coolest things I've ever seen. So one question is that you mentioned this truncation to finite dimensional infinity group. And,
yes.
I'm wondering, like, that's probably related to the model that you want, right? Related to the weights.
Yeah. Yes. Yes.
So in particular, how do we know that we can always truncate to a finite dimensional thing starting from a very infinite dimension?
Yeah. So at least first of all, because the physical ideas that we know, a lot of the details from the continuum. Of course, the continuum QFT is not well defined, but as far as we understand it, a lot of the UV details are unimportant if we consider some IR or not IR limit, but certain energy scale. Then the very UV things are unimportant, right? So first of all, we know a lot of the UV details in the continuum should not be very important. So we should be able to describe the things on the lattice intuitively in a finite dimensional manner, because all those infinite dimensional, like how this curve really wiggles, should be some UV detail, right? That's our physical intuition. And why we know that finite dimensional category is certainly able to capture the topological information. It's simple because the topological classes themselves are finite dimensional, right? They are not even finite dimensional, they're discrete. So certainly you would not need that many details to recover that, right? So I guess, but related to the question is, how do you assign the suitable weights, right? So far that needs to base on the physical intuition, because I don't think in the end you cannot throw physics entirely away, right? You need to know what physical properties the model should have. But what can be turned into a mathematical problem is how to think about the renormalization of the categorical weight in terms of category theory. And yeah, I didn't mention this in the outlook, but that's related to the constructive QFT step, because like how to systematically talk about, I have some vague idea you want to talk about renormalize. So first of all, this weight, roughly speaking, would be, so first of all, we set a few configuration. It's a map from the category of the lattice, or the simplicial set of the lattice, to this simplicial set of the degrees of freedom. So that's the configuration. And then the weight is a map of the configuration to a weight, right, to a complex number, non-zero complex number in general. So that would act, and if the weight is local, roughly speaking, that would be a functor from this simplicial set, or this complex, to non-zero complex numbers. Then, so that would be what a weight is. And then renormalization should be some functor that when you, or some natural transformation, when you consider coarse graining is a functor on the lattice, right? You can build it as like an ADS space in one higher dimension and so on. That would, so the ADS space in one higher dimension is like some simplicial version of functors. And then that would also be, so the weight would, should be able to introduce some, induce some functor in the category of functors from this simplicial, from this kind complex to the weights, to the non-zero complex number. So roughly speaking, that's what should happen. But like how to actually talk about that, I think it's something I want to do in the future. Yeah, I guess, so to describe the weight, you need some physical input from the beginning. But once you have the physical input at some energy scale and you want to talk about renormalization, I think that should have some natural mathematical language. Yeah.
Very nice.
Yes.
And also one last thing to mention is that you mentioned
the what?
The harmonic analysis.
Yes.
Yeah, like you want to get, for instance,
this
characters.
Yes. So yeah, characters. Yeah, basically harmonic analysis is the character, right? Yeah.
So well, first of all, you need a hard measure.
Yeah. Yes.
For lead to groups, it's possible.
But in a simplicial presentation.
Yeah.
Right.
Generalize that.
It
shouldn't be too difficult.
Yeah. So we should talk about. I think this certainly would have an answer. I just searched what people. I think people's directions of working on higher representation nowadays does not seem very helpful for this physical problem, because people are trying to generalize this higher vector space, and there are different notions of higher vector space. But I don't think a vector space is crucial. I think the harmonic analysis aspect, or the character aspect, is the actual crucial thing for physical observables. Yeah. So yeah, maybe we should talk more about that. Yeah.
Thank you.
So what do you mean by lose information, or if you have all this level of LD, then you does not lose information? Yeah, I don't quite understand that. Thanks.
Well, yeah. So it's just should I explain from a mathematical or physical perspective?
I don't know. No, I mean.
No. First of all, let's from a mathematical perspective. So this is a higher category.
Yeah.
And then these are also higher categories.
Yes.
And then because this has a map, there's an inclusion map from here to here, and then there's a known map, like a functor from here to here. So you induce a functor from here to here, right?
Yeah.
You get a functor from here to here. But if you remove the higher morphisms, then, well, of course, the functor will have less information than the original functor.
Yeah, just because
right?
L0 is just a subset of M, right?
Yeah, it's a finite subset of M.
Yeah.
Yes.
Yeah. So my question would be, it seems that each n, for each n, Ln is just a subset of P and M. But then why you suddenly don't lose information when you include all these.
Well, because the d-dimensional cells fills up the continuum entirely. There's no leftover space, right? It's yeah. Yeah, so that's why in general you need to go to dimension D. However, that depends on what topological data that you want. If you don't want that much topological data, maybe you can truncate earlier. But if you want, at least you need to go to dimension D. Yeah.
Okay, I see your point.
I don't think you can go beyond dimension D either, because roughly speaking, a d-dimensional space-time can at most probe that dimension of topological configuration. Yeah. But in general, you need to go up to d dimensions. But if you care about less information, you can truncate away more. Yeah.
Thank you very much. Another question. So can you recover the like lattice models or whatever tensor category language other than those group-like tensor category?
Yeah, the Turaev-Viro you can also do. So Turaev-Viro is beyond group theory.
Yeah.
Sorry. This not. Oh, I hit the wrong button. Yeah. So there was this picture. So if G is a finite group and T is the set of the finite group, then you recover this SPT, like Chen, Gu, Liu, Wen model. And if you ignore the T, you just use the G for finite group, then you get a Dijkgraaf-Witten model. So the degrees of freedom. So in that case, if you ignore the T, you get this the nerve of BG, right? So that just means like on the vertex you have nothing, and on each link you have a group element, and then on each triangle you only specify 2 group elements because they need to multiply to the multiplication of this need to equal to this. Okay, so you only have G squared. You just specify these 2, then this is also fixed. So that would be the Dijkgraaf-Witten model for finite group. Okay, and but you can also generalize this to just some set S, and then you can have some set A that just specifies what are the 3 choices of S here that can appear together in a triangle, and that would be called the admissible condition in the Turaev-Viro model. And the S doesn't have to satisfy something like this. It's a more general, right? So that's the Turaev-Viro model, and yeah.
So I guess you can do the data of like fusion channel.
Yeah. So this is indeed the fusion. So this A is the fusion data, like like this S1 fused with S2 equal to some of things.
Okay, thanks. Thanks very much.
Yeah, so that's what this A describes. Yeah. But the nice thing is using this anafunctor language, let me make one more comment on that. Is that why this is able to describe the continuous degree of freedom beyond just the discrete degrees of freedom. I think one crucial thing is I didn't attach a linear structure in the degrees of freedom itself. So in the definition of tensor category, there's a linear structure that is intrinsically appeared in the definition, right? But here, these are just groupoids. I don't have any linear structure until I map to here. So the linear structure is in here, right? It's in this U1. So I don't need to describe a linear structure in the degrees of freedom itself. And why is there a distinction between this language, such a distinction between this language and the language of tensor category? Because the tensor category language was intended to describe a TQFT. And physically, the TQFT has a feature that the UV is the same as the IR, right? Because the IR are the quantum states, they should have a linear structure. So because the UV is the same as the IR, so the degrees of freedom are also inherently endowed with this linear structure from the IR quantum state. But if you care about general dynamical QFT, the UV degrees of freedom and the IR states doesn't have to have any obvious relation. So you don't need to define a linear structure to begin with in your degrees of freedom. But when you talk about these general observables, the linear structure will appear somewhere in the middle steps So I think that's why this can go beyond the tensor category language, but recovers it also. Yeah. So I think the proposal, roughly speaking, is to give away the linear structure in the definition of the stuff to begin with. Yeah. Uh-huh. 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 Yeah. Yeah. Yeah, and I also want to make another related comment that is in this kind of definition of lattice QFT, because you need to specify, because you have a lattice model, right? So it's fully extended in a certain sense. You know what are the vertex, link, and so on, degrees of freedom. So it's fully extended in a certain sense. But the non-trivial thing, as we said, is that there is a weight. That is what makes things non-trivial. So in general, for example, Cairo-Chern-Simons cannot be fully extended. And on the lattice, I just said I can realize the Chern-Simons Maxwell theory on the lattice. And the key is you can, in some sense, show that the Maxwell term is necessary. And the Maxwell term is not purely topological. No matter how large, how small it is, it's non-zero. So you have to have some non-trivial dynamical weight. That is the non-trivial weight in the path integral. First of all, it's physical, and also it's what makes everything fully extended. But the price is that you have a weight that is not always 0 or 1 or complex space. You have a weight that is in general not just a complex space. It has some real part, some modulus part of the weight. But that's physical. Yeah. Yeah. Yeah.
So because the instantons can have a size and shapes,
yes.
I was a bit skeptical about what you did. And then I realized that there's different gauge called the singular gauge, where winding numbers are all at one point. And then configuration falls off faster than putting the winding number especially. So in some sense, I guess this what you are trying to do instantly is like localize the winding number point into somewhere in your whatever.
I would say it's not quite. So that instanton can have different size and shapes in this construction.
Yeah, so I'm saying the singular gauge means the singularity is at one point, but instanton configuration itself is spread.
Yes.
It's just
yes, it's indeed, it's somewhat related to that, because in the model, it's similar to the V-line model. In the winding, like for example, in this example, we feel that this has a high probability of winding number 1. And indeed, the winding is spread over the circle, right? Everywhere has winding 2 pi over 6. However, if you write that M configuration, for example, the M would be M equal to 1 here, and M equal to 0 elsewhere. Right, if you choose theta from -pi to pi. So it seems like the M contribution is only on here, but the gamma is actually equal to 2 pi over 6 everywhere. But it's just that gamma equal to d theta plus 2 pi m. And if you fix theta from -pi to pi, then it turns out that everywhere else m is 0, but here m is 1. I think that's what you said. Yeah, so this is, Yeah, so these are all the ideas from V-line model that the philosophy from V-line model agree with that. Yeah. Yeah. Yes, this lambda. Yeah, so this what actually yeah, this thing is this thing, if you ignore the t, because we said, roughly speaking, because we said we need to respect the embedding of this into here. So when you consider natural transformation, you ignore the t, okay? If you ignore the t here, this will just be an anafunctor from BG to BBBU1. And that's a multiplicative bundle gerbe, which is also a two-group U1 two-group BU1 extension of G, and it has other names as well. Yeah. Yeah, this is the multiplicative bundle gerbe. So compared to gerbe, it has an extra structure because G is also a group. So it has a multiplicative structure. And you also need to realize the multiplicative bundle gerbe in a nice enough manner. First of all, it needs to be finite dimensional. And also it needs to, for the lattice model to respect certain global symmetry or gauge invariance. The Y has some condition, like we said, things should only depend on the eigenvalues in G, not the eigenvectors, and so on. So there are some extra requirements. Yeah, but this is a multiple bundle gerbe. But I think what this algebraic as well as the geometrical idea that tells us is that you can also go beyond gerbes in general. In general, it's just you consider such an anafunctor, right? So if you want to capture like H4 of BG in Z, that would be the multiple bundle gerbe. But if you want to capture more general things, it's the same idea, just construct such an anafunctor, right? So maybe in general, this thing in the middle has not been constructed, but at least the goal is clear. Yeah. Yeah, how you come up with this is, yeah, this is the place where, okay, there are, of course, in category theory, many things can serve the thing in the middle. So we want some property like the Y only depends on eigenvalue. And here you can see that this Y has some like plus and minus one are special points, but that only depends on eigenvalue. These are actually the places where you have eigenvalue degeneracy. Okay, plus and minus ones are where SU2 matrices has eigenvalue degeneracy. So so first of all, there are some general requirement like Y should only depends on eigenvalues. And then how you come up with this, indeed you need some things that cannot be answered by category theory. You still need some concrete work, right? So you need the category theory gives you a principle of what you want, but you still need to do some concrete work. How to construct the Y, how to construct the multiplicative structure lambda, and how to construct the lattice weights, you need to have some physical intuitive input. But some very nice thing is the physical intuitive input not only answers these things for you, also when you deloop these things for gauge theory, the physical intuition also solves the Yang-Basta equation for you. I think that's very beautiful. Yeah. Yeah.
General construction need just anafunctor construction and then you can if you go to discrete cases like Turaev-Viro or Jing-Yuan, you just specialize this anafunctor.
Yeah, this in the discrete case, this Y can just be G. In the discrete case it becomes very simple. Just lambda has an extra U1. Y will be the same as G, and lambda just has an extra U1. And so on. Yeah, it will be very simple. Yeah, and then it will just very simply recover the Turaev-Viro model. Yeah.
Okay.
Yeah. Okay, thank you for the opportunity.